as you get more comfortable with function notation, you'll find out that you'll find out that we really use the condensed form the most. So since a lot of times we are working with equations, it just makes sense to do that. But it doesn't necessarily mean that you always have to use function notation. Function notation is just a way to simplify the amount of writing that we have to do. So let's take a look at an example where we'll build a model and then we'll use function notation. So this one says the price for a white t-shirt is $6. For every shirt purchased in bulk over 100, a discount of 1 cent is given for each shirt. So for each shirt, so if I purchase 101, then I get a penny discount, so I'll only be paying $5.99 per shirt. If I buy 102, then I'll be paying $5.98 per shirt. Write a model, in this case an equation, that gives the price, which we'll use a P to represent, for each shirt as a function of the quantity of shirts purchased, and we'll use Q to represent quantity. Okay, so the first thing I always like to do, if I'm not sure, I'm going to build a table. So I want to basically, this says price as a function of the quantity. So I'm going to write it in function notation to express what I want to do. So output is a function of input. So that means I'll put my input over on the left, my output on the right. So I know that if I'm going to buy, first of all, I have to buy at least 100 shirts in order to be able to get the discount. So it doesn't make sense to talk about anything below 100, because anything below 100 I'm going to pay $6 per shirt. So $100 shirts will cost me $6 for each shirt. If I buy 101, well, that means I'm going to get a 1 penny discount, which is 0.01. That's how we write 1 cent, and that's going to be $5.99. Okay, if I buy 102 shirts, it's going to be $6 minus 2 cents. So I'm only going to pay $5.98 per shirt. 103 is going to cost me $6 minus 3 cents equals $5.97. And so on and so forth. So we start to see the pattern. Well, how am I able to get $5.99? Well, I'm subtracting off multiples of 1 cent. So to get the price, I start with $6. The $6 is going to decrease by 1 cent. But it's going to decrease by multiples of 1 cent. So, for example, I notice that when quantity is 1, then 1 times 1 cent is what I remove. When quantity is 102, then it's 2 times 1 cent. If quantity is 103, then it's 3 times 1 cent. So I'm really only taking the amount of shirts above 100 and multiplying it by 1 cent to determine my discount. So what I have to do is take the number of shirts, subtract away 100, because, again, if it's 103, I'm only taking 1 cent times 3. So if this were 103, you would do 103 minus 100 is 3, and that would accumulate for a discount of 3 cents. Okay, so that means that this is how I'm able to get or figure out what my new cost is going to be, or my new price for each shirt. So in function notation, I would write P, the price is a function of quantity, and I can calculate it by taking $6 minus 1 cent discounted however many shirts I buy above 100. Again, remember, this only works for values above 100. For example, if you plugged in a quantity of 100, well, in the parentheses you'd get 100 minus 100 is 0, so you get 0 discounts of 1 cent. If you plugged in 101, then you'd get 101 minus 100 is 1, and you'd only get 1 discount of 1 cent, giving us $5.99. So it appears that it works. The next thing to think about is a domain and range in this problem, and this problem is particularly important. So domain is the set of all possible inputs that can be used. A range is the same thing, except it's the set of all possible outputs that can be used. So in our situation, we know that our input, so our domain,